Chemical equilibrium, a wonderful chapter for IIT exams and NEET exams. One question mandatory in all these, and the topic is very, very, very simple. Okay, now chemical equilibrium chapter is very simple. Ionic equilibrium is little lengthy and tricky, but chemical equilibrium is very, very simple. The numericals you need to apply some logic, but rest part is easy. So first of all, you should know what is chemical equilibrium. For that purpose, you should know what is a chemical reaction. Let us say if A is converted to B, A is converted to B, but B to A is not possible. That means only forward reaction is possible, no backward reaction. Backward reaction is not possible, only forward reaction is possible. Then this type of reactions are called irreversible reactions. Okay, now irreversible reactions you can take like neutralization reactions. Okay, now H2SO4 plus 2NaOH gives rise to Na2SO4 plus H2O. This is a neutralization reaction, or you can take explosion reactions. Okay, now precipitation reactions, all these reactions are irreversible. And then reversible reactions. In reversible reactions, what actually happens is, for example, CaCO3 gives rise to CaOCO2. And if you are doing this process in a closed container is mandatory here because this is solid, and this is gas. Now CaO and CO2 can react back to form CaCO3. This is forward reaction, this is backward reaction. There is forward reaction as well as backward reaction. Remember, whenever gaseous reactions are there, that must be in the closed. Okay, now in this lesson, if I am not going to mention closed container, means by default you have to consider that I am discussing about closed container. Okay, otherwise PCl5 gives rise to PCl3 plus Cl2. These kind of examples you can take very comfortably. These reactions are called reversible reactions, in which reactants can be converted to products, products can be converted back into reactants under some specific conditions, right? So our chapter is related to only reversible reactions. Reversible reactions, so many conditions will be there. We need to be very careful. Okay, now whether that is carried out in a closed container or not, and particularly states mentioning time, you must be very careful, because in all your numericals they play very, very important role. Remember. Coming to forward and backward, let us say a reaction is taking place like this. A plus B gives rise to C plus D. It's a chemical reaction which is taking place in gaseous phase, right? So this I am writing like this: A moles of A, B moles of B, C moles of C, and D moles of D. These are reactants and these are products. Two sides arrow is there, means forward reaction, backward reaction, both are possible. Now what happens is, forward reaction is A and B reacting, that is forward reaction. So rate of forward reaction depends on concentration of A and concentration of B. A number of moles are small a, make it as power. B number of moles are small b. Simple. See again, rate of forward reaction is directly proportional to A to the power A and B to the power B. Now what we can say is the rate of forward reaction is, in place of proportionality mark I am keeping n is equal to mark, and kf, forward na kf, into A to the power A and B to the power B. This is for forward reaction. These two lines we are discussing for forward reaction. Come to next. Rate of backward reaction is directly proportional, again concentration of these products, so that you can say C to the power C and D to the power D. When square brackets are there, this is concentration, or this is equals to KB backward, C to the power C, D to the power D. Fine. So the question is, what is equilibrium? Equilibrium means rate of forward reaction is equal to rate of forward is equals to rate of backward. When rate of forward reaction and rate of backward reactions are same, that particular state is said to be equilibrium state. Equilibrium state means the rate of forward reaction and rate of backward reaction must be same. So rate of forward reaction we can take from here, that is Kf into a to the power a, b to the power b is equals to backward c to the power c, d to the power d. Now what we'll do is we'll bring this constants one side. Kf by kb is equals to concentration of c d by a and b. Correct? Kf is a constant, Kb is a constant. Together these two constants are called equilibrium concentration constant. Equilibrium concentration constant, that is equals to C D by A and B raised to their stoichiometric coefficients. This is the expression. Fine. Like this, when you are writing, it is called law of mass action. Whatever you have written, that is only called law of mass action. Kc is equal to concentration of products raised to their stoichiometric coefficients divided by reactants raised to their stoichiometric coefficients. If you want, I will give you one more line. For example, PCl5 gas converted to PCl3 gas and Cl2 gas. For example, this is given. Then Kc is equal to, these are the products, concentration of PCl3, concentration of Cl2 by concentration of PCl5. Like this you can write. For example, you have CaCO3 gives rise to CaO plus CO2. But these two are solids and this is the only gas. So Kc is equal to concentration of CO2 only. Solids are not taken. Solids concentration is taken as unity. So there is no need to consider these solids. One more reaction just for your idea. NH4HS ammonium bisulfide, which is a solid, gives you NH3 and H2S. Both are gases. So Kc is equal to concentration of ammonia, concentration of H2S. Not, this is not considered. Just note this point. Like this, when you are writing, it is called law of mass action. Here I have mentioned all these concentrations. You can say in terms of pressure also. Then that is called Kp. Then Kp Kc relation, how to write Kp and all, we will discuss in part 2 of this chemical equilibrium. Thank you.